Hey class, welcome back to the lesson on tangent lines. Hopefully you've seen the first two videos because we talked about pretty much everything except for one thing. We identified what a tangent was, we found out angle measures, we found out some distances, we even found a radius using crazy algebra, and now we're going to talk about is incircles. Okay, so if you remember incircles, like from angle bisectors, where angle bisectors intersect in a triangle, the incircle. We're going to talk about that in a second. But what does incircles have to do with anything? It has to do with this next note on tangent lines. So there's a theorem involved in tangent lines. And now we're going to talk about, instead of one tangent line, two of them. So if we have two tangent segments to a circle, if they share a common endpoint, right? So if from an endpoint somewhere outside the circle has two segments that are tangent, then the two segments are congruent. So the measure of AB is equal to the measure of CB. That's the case. So you might see this pop up, but what you also might see is a reminder about tangent lines from the previous note. Remember, tangent lines are perpendicular to the radius. So in this diagram, to note, what we don't see is the radius, but we still have to remember it's there, dude. We can remember that there's still tangent lines, and this comes back. So there are tangents to the radius. This comes back to a lot of things. And you can see now we have two congruent triangles, by the way, hypotenuse-leg theorem of congruency, because we had the segment in between. We now have two congruent triangles. We can either call it side angle side because the radius is the same. We can call it hypotenuse-leg because of the reflexive property. There's all sorts of neat things that we can do to talk about these triangles are congruent. But anyway, if two segments are tangent and they meet at an endpoint outside the circle, then the segments themselves are congruent. So what does that have to do with anything? Well, it has to do with incircles. It has to remember what an incircle is. It's inscribed inside a circle, or a polygon is circumscribed around it. Okay, so here we go. This is what we're talking about. So if you remember this, it's telling us right now, circle O is inscribed in the triangle. That means it's tangent on the three sides of the triangle. Okay, so it's telling you it's tangent to the three sides of the triangle. And the question now is, what is the perimeter of triangle ABC? So you look at this and you might be confused. You might think, well, let me just draw some radii and make a whole bunch of right triangles. Yes, you can totally do that. You totally can. There's nothing to stop you. But what we have to remember is the note we just talked about. Remember the note. If there are, or there is a point existing outside, you have the two tangent segments to that circle, those segments are congruent to each other. So what does that have to do with this problem? Well, let's take a look. How about just take a look at AD, right? If we take a look at AD and we cover up the rest of the figure, what do we know? So based on that note that we just saw, if we cover up the rest of the figure, what do we know? If the distance from A to D is 10, guess what else is 10? The distance from A to the other tangent. So this is also 10 centimeters. Okay, so we have to know that from the note. All right, so isn't that interesting? So the same thing happens when we cover up everything else. Look at what else is going on. Take a look from endpoint B that's outside the circle. If we cover up the other garbage, from B to D is 15 centimeters. Guess what that means from B to E? Another tangent. Because it's an incircle, that distance is also 15 centimeters. And the same thing applies to what's happening down here. If this is 8 centimeters here, well then guess what? It is from C to E, 8 centimeters as well. And now what we can do is find the perimeter of the triangle. So we have our triangle that's ABC. I'll redraw it. The distance from A to B is 10 and 15. The distance from A to B is 25. The distance from B to C is 8 and 15, which is 23. And the distance from A to C is 10 and 8, which is 18. So we have our three sides of our polygon. We find perimeter by adding them all up. So we do 25 plus 18 plus 23. And let's see, we do some old school math. 8 and 3 is 11 and 5 is 16. Carry the 1, that's 66 centimeters. So the perimeter is 66 centimeters. And that's how that works. So it's all based off of that simple yet complicated note that if two lines are tangent to a circle from a shared endpoint, okay, from a common endpoint, then those segments are congruent. So let's see if we can make this a little bit more challenging. and I bet we can. Yeah, we can. So let's do that. I like making things more challenging. So here we have, we're going to find the missing segment length of the quadrilateral circumscribed about the circle. So notice before we talked about the circle being inscribed, well, we can also have a polygon being circumscribed. It's the same type of principle. What it means is tangent on all faces, tangent on all sides, I mean. So we know we have tangent stuff. Now, take a look at this. This is what is interesting. The only piece of a segment that we're given is 1.9 inches here. So what does that mean? It means according to the note, remember according to this note, if we start hiding stuff, we start figuring out other distances, right? So if I hide the rest of the figure, I know the whole way across is 3.4, but what's this measurement right here? If this is 1.9 here, what's this measurement? 1.9 as well. Very good. Now, the challenge is that's the only measurement piece I have, right? Well, no, because the entire length is 3.4, and this is 1.9 here, so that must mean this is what's left over if we subtract 1.9 from 3.4, which should give us 1.5. Is that true? Yeah, 1.5. So we should have 1.5 here. That's our distance here, 1.5 here. Now, again, if that's 1.5 here, and we're talking about a shared endpoint, what's the distance here? 1.5. Right? So that's uncovered. Okay. Now the only question is, well, what's this distance out here? Well, darn it, the whole way is 3.6. This is 1.5. This must be the leftover. So if we subtract 1.5 from 3.6, we get 2.1. So this is 2.1 inches here. Now if it's 2.1 inches here, again, because of the note, if we cover up some stuff, we will know that this is also 2.1 inches here. Isn't that neat? And if that's 2.1 inches here, well, what are we missing this little piece? We subtract 3.7 minus 2.1. Gives us 1.6. So this is 1.6 here. And if this is 1.6 here, this is 1.6 here. And now we can find our perimeter. So the entire perimeter of the quadrilateral. On the top part, what we didn't have is 1.6 and 1.9. That gives us 3.5. On the right-hand side, it gave we have that from the beginning, 3.4. On the bottom, we had that from the beginning, 3.6. On the side, we had that from the beginning, 3.7. So to find perimeter, we just simply add up everything. And feel free to use a calculator. So we'll do that. All right, let's clear that out. All right, so what did we say? 3.5 plus 3.4 plus 3.6 plus 3.7 equals 14.2. So there is our perimeter, 14.2 inches. And that is how we find perimeter. So that's it for tangent lines, folks. So we found out about tangent lines. Remember, there are two key notes. The first note was that tangent lines are perpendicular to the radius. They touch at one point, perpendicular to the radius. And if we have two tangent lines from the same endpoint, the distances to the circle are congruent. So that's it for this lesson. Hopefully you enjoy it. Get some work done. See you guys on the flip side.